Okay, welcome back to From Zero to Zeta. I'm your host, Rowan McKee, and before we dive in, a few quick announcements. So I set up a website for resources, scheduling, and links to everything else I'm working on. Visit From Zero to Zeta. You should see it down there. I also started a Discord server so that people can come ask questions, participate in discussions and events. You'll see the invite link down in the description and scrolling across here. I also started a gaming channel, casual gaming. It's called Zero to Zeta Gaming, and in it I also play chess, which has been gaining in popularity. So some of you, especially from the math crowd, some of you may be interested in my chess games. I'm about 1600 rating online and working my way up. I also do math tutoring on the side. And if you need help with math formatting, I got you there too. I've been using LaTeX for approximately 12, 13 years now. So I'm pretty practiced at it, and I've been tutoring for almost long. Please reach out to me if you're interested in tutoring or LaTeX document preparation. Another thing I've been doing is occasionally post quick test prep short. So you'll see every so often I post a short. I'm wanting to increase the frequency of that a bit. And so if you're preparing for the GRE, definitely go check those out because you will find those helpful. And also thank you to everyone who's already subscribed to the channel. If you haven't yet, please like and subscribe. It really helps the channel grow. And today we're moving from intuition to notation, a mathematical language that makes group theory precise. So previously we built up the intuition behind groups, what it takes to be a group, closure, associativity, an identity element, and inverses, the undo. Concrete examples were integers under addition, symmetries, and permutation. Modular arithmetic as a standard model for finite group, specifically finite cyclic group. And we talked a little bit about what is a cyclic versus not a cyclic group, and what does it mean to be abelian. And we also talked about subgroups that live inside larger groups. And today's step is to develop the notation to let us express these ideas quickly and unambiguously without having to explain each bit of notation along the way. Mathematics and mathematicians use compact notation to make ideas precise. Each symbol has a purpose. Let's walk through the essentials. So first we have set builder notation. H is the set of all integers x such that x even. The vertical bar means such that. This describes infinite sets in one line. So for instance, this set H, that describes all of the even integers because it includes x for whenever x is an even integer. You may have seen how to subtract numbers in grade school. When it comes to sets, the operation is a little bit different. We don't do element-wise subtraction. That is not how subtraction is defined in this setting. A set different is describing, well, if we have two sets A and B, A minus B would be describing the elements that are in A but not in B. A minus B will be a subset of A, but not necessarily a subset of B. And B minus A will be a subset of B, but not necessarily a subset of A. The example I've just shown you shows you the non-overlapping parts from each side. So how A minus B and B minus A can be, completely different. The cardinality. When we say cardinality, we're talking about the size of a set. The cardinality of the real numbers, that's infinite. Cardinality of the integers, that's infinite. The cardinality of a set A is the number of elements in A. The set 1, 2, 3 has cardinality 3. The set A, B, C, D has cardinality 4. And the cardinality of the empty set is 0. And we use this little symbol to denote the empty set. And we use this sort of E-like symbol to denote membership. So we say 2 is in 1, 2, 3, but 4 is not in 1, 2, 3. A is a subset of B, means that every element of A is in B. We sometimes write A is a superset of B, which just means that A contains B. That is considerably rarer than the other one, however. Usually you just flip the order and be done with it. A number of abbreviations that come up, especially when dealing with proof, are ST, such that, WRT, with respect to, IFF, if and only if, which denotes a two-way implication, or as we'll see later, a bijection, and then W log, which stands for without loss of generality. So, for example, how Y changes WRTX means we are measuring change in Y as X varies. And of course, how could I forget these two symbols, for all and there exists? You can remember these sort of as like the for all looks like an upside down A, and all starts with A. Similarly, there exists looks like a backwards E, and exist starts with the letter E. Another thing I want to cover is congruent. Sometimes when we say two things are equal to each other, we don't necessarily mean that they are identical. We mathematicians like to generalize the notion, like, what do we mean by equal, really? In a lot of cases, it can help to equate things from two different sets that you may not normally think as being the same, and we call that an equivalence relation. Second episode, the episode on axiomatization, we're going to do a little bit of that here to sort of work out what it means to be an equivalence relation. So first, we have the reflexive property, the reflexive axiom. For an equivalence relation to be an equivalence relation, it needs to have that any element is equivalent to itself, right? That makes sense. And we also have a symmetric property. This is sort of like the reflexive takes it 0 steps, the symmetric takes it 1 step, and the transitive takes it 2 or more steps. With the symmetric, we have if A is related to B, then we must have that B is related to A. The transitive step, if A is related to B and B is related to C, then A is related to C. That's all it takes to be an equivalence relation, which gives us a tremendous amount of power when describing a certain structure. If the elements aren't equal in the traditional sense, like 1 equals 1, fine. But if we're saying that 17 equals 2, that's a little bit less clear on what we mean by that. So we use a third bar over the equal to say, oh, it's actually this generalized form of equal, and we call it congruent. So 17 is congruent to 2 mod 5, that sort of thing. The next thing I want to talk about is functions. Functions play a pivotal role in group theory. A function assigns each input into its domain to exactly one output in its codomain, and I will unpack what that means. We have this function notation. Function, what's the name of the function, colon, where is it coming, where is it bringing elements from, and where is it taking elements to? You're a construction manager, and you need boxes moved from one place to another. Well, the first place, that would be your set A. The second place, that would be your set B. And the movement of those boxes is the function. The set of inputs on which f is defined, a function must give an output for every element of its domain. The domain of f from A to B is A. And the target set where outputs live, not every element of the codomain must be hit. And the codomain of f from A to B is B. We arrive at something called the image, and that's a slightly smaller set than the domain, and doesn't necessarily have to encompass the whole function, but the set of outputs that actually occur is the image of f, and it will be a subset of B. It could equal B, but it doesn't have to. So for example, f of x equals x squared with a equals r, and b equals r has the image from 0 to infinity, because you're not going to get any negative numbers. The domain has no unused elements. Every input maps somewhere, but the codomain can have unused elements. In this case, the negative number. A function f is invertible if there exists another function f inverse going from the codomain to the domain, such that for every A, we have f inverse of f of A equals A, and f of f inverse of A equals A. Example is f of x equals x plus 3. Has the inverse, well, you can subtract 3. However, f of x equals x squared does not have an inverse because if you try to, say, plug in the inverse of 9 to x squared, well, you get something like plus or minus 3. And that is 2 outputs for 1 input, which the definition of a function does not allow. F of x equals x squared does not have an inverse. But there is a term that can help us fix that situation. If we have any element y in B, the pre-image of that y is a set of inputs that map to it. So, and we mathematicians, we're not very creative. We like to use the same notation over and over again, and it means completely different things every time. So we still use the notation f of f to the negative 1, but what makes it different is that the inside, what we're plugging into the pre-image, is a set rather than an element. So the pre-image of f with respect to y is a in A, such that f of A equals y. Pre-images can have many elements even when no inverse exists. The difference is that an inverse is a function, while the pre-image need not be. So the inverse must give one output for every input, but the pre-image need not return any output for a given input, or it may return many. The next few terms I want to talk about are injective, surjective, and bijective. Injective, you may have heard this term as one-to-one. It means that for any two elements, A and B, if a function f of A equals f of B, then that tells us that A equals. Surjective is kind of like the other direction. It says that for every element in our codomain, we must have something in our domain that maps to it. It just makes sure that all of the elements in the destination are used. And a bijective function, or invertible, means that the function is both injective and surjective. It's both one-to-one and onto, and that is what guarantees an invert. For instance, you might think that injectivity is only required to get an inverse, but without surjectivity, then when you flip the domain and codomain, you get some elements that are not used in the domain, and that's not a function. And just to preview a little bit, a bijection that also preserves the group operation is called an isomorphism. We'll be getting into that a bit later. Final part of this is I've been talking a lot about function composition. That is one of the key parts to being a function, is that we can compose them. Without composition, there is a lot of structure disappears. What we say is if f is a function going from A to B and g is a function going from B to C, then g of f is a function going from A to C. And you might recognize a pattern here because it's the same sort of language we used when we talked about the transitive property in the equivalence relation a little bit earlier. Functions can and do form groups, and different families of functions can form different families of groups. In particular, we can set up an equivalence relation between functions, and we often do. For any function, they're equal when all of their outputs are equal at the same input. So if f of 2 equals g of 2 and f of 3 equals g of 3 and so on, then we can say that f equals g. So we get the same sort of pattern that allows for us to use equivalence relations with functions as well. So now I want to dive into some conventions and some popular notation that we use when we talk about group theory. So for example, capital letters typically denote set or group. Lowercase letters denote element. Capital G, capital H, those are sets or groups. The lowercase g and h might be elements of a group G. And this convention is so widely used that violating it often causes confusion. As we've seen from previous episodes, each group has an identity element. We usually call that element E. Element starts with the letter E, I guess. Inverses with the little -1 in the top, yeah, that's an inverse. So, each G in a group has an inverse G to the -1. That's an inverse. We get into something we talked a little bit about last time when we were going over cyclic and non-cyclic group, and how any element, when applied repeatedly, will generate a subgroup. And so conveniently, there is notation to describe that happening. So starting from a single element G, the set of all repeated applications of G and its inverse forms a subgroup pointy brackets G. The pointy brackets G here, and then this one. Now, the first is more compact and more widely used and understood. It glosses over a few nuances that I want to cover. Throughout grade school, we're taught, anything to the 0 power is 1. That's because we're working with the real number. Okay, so this exponentiation isn't the same as that one. So for instance, if our group G is the set of integers mod 5 and we're using addition as our operation, then the inverse of 1 is -1, and G to the 0, that's 0. The inverse of 0 is 0. This notation can be a bit confusing if you're coming from a context where exponentiation works like in the real number. So I've provided this second notation to make it a little bit clearer on what's going on. So in additive notation, this is all integers multiples of G. In multiplicative notation, it's the exponentiation you are already familiar. Another thing I want to touch upon is the order of a group and its size written a G between bars, just like the cardinality, what we were talking about earlier, and the order of an element, which is effectively the size of the generated subgroup that the element G generates. And we represent that with the same notation except with the lowercase g. Here's a big reason why the conventions are important to follow and understand. Capital G in between vertical bars represents the size of the whole group, but lowercase g in between vertical bars represents the cycle length of a single element. Like I said before, we'll take a look at this later, but when two groups G and H are isomorphic, we do use the congruent sign to equate them because isomorphism does follow an equivalence relation. If two groups G and H are isomorphic, there exists a bijection G to H, preserving the group operate in this fashion. We'll return to structure preserving math later. And the last thing I want to go over is I want to give you the tool to describe what's going on in groups. So we're going to explore different ways of drawing groups. We're going to use something called a Cayley table, and we're going to look at something called a Cayley graph. They are related. They describe the same structure, just in different ways. Cayley tables is a grid recording the results of the operation for each pair of elements. It can get quite large pretty quickly. For example, if your group has 10 elements, then the Cayley table will be 100 entries, 10 across, 10 down. We arrive at this definition for finite G in the set from G1 to Gn. The entry ij is Gi times j. Here is an example of a Cayley table for the integers mod 6 under addition. And here's one for the Klein 4 group, also called Z2 cross Z2. We haven't discussed that much, but that cross, that's called a Cartesian product. Basically just adding components it's adding a number of outputs. So Z2 cross Z2 is just the integers modulo 2 under addition, and then another entry of the same type. The Cayley table for that looks like this. Last time we were also discussing permutation groups. So we have S3, which has 6 elements. You'll recall that it is not cyclic. Here's the Cayley table for that. And the next thing I want to talk about is a Cayley graph. The definition, KGS, has vertex set G. For each G in G, S and S, draw an edge G to GF, often colored by S. Different generating sets S yield different drawings of the same group. Z mod 6 with generator 1, we get this diagram. With Z2 cross Z2 with generators 1, 0 and 0, 1, we get this one. And we get this diagram with S3 for generators 1, 2, 3 and 1, 2. It will slightly different if you just change R to 1, 3, 2. It will look slightly different, but it still represents the same group. So which to use when? Tables are great for algebraic check, identity row column, inverse positions, symmetry, commutativity. Graphs are great for intuition about generators, word length, and how elements move. The choice of generators changes drawing, but not the group. So today we moved from intuition into the language of group theory. We began with mathematical shorthand, set builders, symbols, and common abbreviations. Then we developed functions, domain, codomain, image, inverses, preimages, and injective, surjective, bijective. Next, we set standard group notation, capital letters for groups, lowercase for element, identity E, inverses G to the -1, generated subgroups with pointy brackets, and the distinction between G and G. We also saw how bijections match sets element for element. Finally, we practiced with Cayley tables and Cayley graphs as complementary visual tools. With the episode, you've equipped yourself with the language of groups. From now on, when you see generated subgroup, order of an element, or bijection, you'll know exactly what that means, and you'll have the tools to express it clearly. Looking ahead, next time we'll put this language to work. We'll study cosets, which partition groups into neat parallel slices, and we'll work with equivalence relations, which formalize the idea of belonging to the same class. How equivalence relations lead to something called equivalent classes, which let you partition a certain set in an equivalence relational way. These ideas open the door to results like Lagrange's theorem. And before we wrap up, if you enjoyed this episode, please like and subscribe. And to keep the conversation going, join our Discord, link in the description. So next, here are some exercises for you to try. You may want to pause between each exercise because a solution will be shown right afterward. And let me know in the comments how you drew them. Exercise 1 is make a Cayley graph for Z12 with the generators 5 and 6. We place the 12 elements on a circle. The generator plus 5 yields a directed 12 cycle, since 5 and 12 are coprime. And the generator plus 6 is an involution, which means it's just back and forth. It's essentially Z2. So those edges are undirected pairing across the circle. Our diagram looks like this. If you drew it differently, let me know in the comments. Let R denote the real number, and Z the integer. Which of the following functions are injective, surjective, bijective, not even a function? A, f is from R to Z, and f of x is the floor of f. The answer? It is surjective, but not injective, because 1.01 and 1 both lead to the same integer. B, g from the integers to the real numbers, with g of x equals 5x plus 1.3. It's injective, but not surjective. There is, in fact, no way we could make a surjective function from the integer to the real numbers. So really, it's just a translation of the integers. It doesn't lie in the integers because we have this 1.3 that makes it so it has to be a real number. Next one is h from the real numbers to the real numbers, where h of x equals x squared. It is neither injective nor surjective. It is not injective because it maps all numbers except for 0 to the same number twice. 9 comes from both 3 and -3, and 4 comes from both 2 and -2. Since there's more than one input going to the same output, it's not injective. And it's not surjective because it doesn't cover all of the real numbers. For instance, -2 is never mapped to from this function because it's negative. Any negative real number will not be hit. Okay, the next one, j from r to r. J of x equals x cubed. This one is bijective because the power of x is odd. So we get the full range. Everything's hit exactly once. Nothing is not hit because a -1 cubed is still -1. The next one is k from the real numbers to the real numbers, taking out 0, where k of x equals 1 over x. This one is not a function at all because it is undefined at x equals 0 in the domain, and we have not included that value in the domain. K of 0 doesn't return anything, and a function has to return exactly one output for every input. So this is not a function. F. M from the real numbers minus 0 to the real numbers, where m of x equals 1 over x. Okay, this one seems very similar to the last one, except we switched our domain and codomain, which means now we no longer have to worry about dividing by zero. So this one is a function. It is injective, but it's not surjective because we didn't exclude zero from the codomain, and zero is never mapped to. If we excluded zero from the codomain, then it would be a bijective function. Thank you. I will see you next time, and don't forget to like and subscribe.